So now we're moving on to geometric sequences and series. We looked at arithmetic the other day, whenever you did that, and saw that it was a sequence being built by adding the same number each time, which we call D, or difference. Geometric sequence, same idea. We're going to see a lot of the same concepts here, but this time there's a common ratio that we're going to call R to get from one term to the next. So basically, instead of adding something to get from one term to the next, we're going to be multiplying this thing. Okay, so a geometric sequence is built upon multiplication. Now, if an arithmetic sequence in which we added was like a linear function, do you know what a geometric sequence is? And hopefully you do, and you're saying, hey, that's just exponential. And you're right, it is just exponential. So that's the idea that we'll be using with geometric sequences. So when we go to write the general form of a geometric sequence, when we go to find that an, we're going to write it like an exponential function. So a sub n equals a1, or your first term, multiplied with r, which is that number you're multiplying to get from one term to the next. And then the exponent on r is n minus 1. So this should hopefully make sense. If you're trying to find the 8th term, you're going to start with your first term. You're going to multiply by r, but you only need 7 r's to get from the first term to the 8th term. So that's why that n minus 1 is up there. It's not n, it's n minus 1. Okay, so let's go ahead and apply that to a couple sequences here, and then we'll go ahead and find A8. So the first sequence, 2, 8, 32, 128, just like with arithmetic, I want to make sure that this is actually a geometric sequence before we go through all the work. Okay, so looking from the 2 to the 8 and the 8 to the 32 and the 32 to the 128, you can hopefully see that, yeah, we are just multiplying by 4. So that means that r equals 4 for this geometric sequence. So now we can find an an, which is that expression that it's asking for. So an equals a1 times r to the n minus 1. A1 is just 2, r is 4, and then I need an n minus 1. And we've got our expression. Okay? Think about order of operations. You cannot multiply the 2 with the 4 because of that exponent that's attached to it. So there's no simplifying we can do with this expression. So let's go ahead and find A8. So that would just be 2 times 4 to the n minus 1, or 8 minus 1, which is 2 times 4 to the 7th. And you can pull out a calculator and find that. I don't have one at my table here, so I'm going to skip that part. But we would go ahead and multiply that together and find that 8th term, which is probably pretty big. Okay, letter B. Again, we have a sequence, 6, 3, 3 halves, 3 fourths. I want to make sure that this is geometric. So let's see what kind of r value we would have. To get from 6 to 3, again, thinking about in terms of multiplication, we'd be multiplying by a half. So does that stand true for the next two? From 3 to 3 halves, again, yeah, we're multiplying by a half. From 3 halves to 3 fourths, there's another times a half. So this is, in fact, geometric with r is a half. Okay, so we can go ahead and find an, would be a1, which is 6, times r, which is a half, to the n minus 1. And again, no simplifying can be done, that's it. But now I can go ahead and find A8, which would be 6 times a half to the 8 minus 1, or 6 times a half to the 7th. Now, I'm, again, not going to multiply this all out because I don't have my calculator, but I do want to think about what 1/2 to the 7th is, because you're going to have to do some calculations with fractions, and I expect you to use the fractions. So I'm going to change this to 6 times a half to the 7th means both the 1 gets the exponent and the 2 gets the exponent. Okay, that exponent goes with both numerator and denominator. So this ends up being 6 times 1 over 2 to the 7th. And again, I don't know what 2 to the 7th is. You can find it, but it looks like our answer would be 6 over whatever that number is. One last thing before I stop this screencast. When you are entering something like this on Desmos, you're going to have to type it in, and it's not a big deal, but 2 times 4, create your exponent. Your n minus 1 will have to go in parentheses in the exponent. Otherwise, it'll just raise it to the n, and then you'll end up subtracting 1. So put that exponent in parentheses if you have multiple terms up there. So now let's take care of some sums in geometric sequences, or if we're summing them, we can now call them series. Sum of a finite geometric sequence, you're going to see below here on the screen that there's there's actually two options for geometric. You can sum a finite sequence, which makes sense. If you have 12 terms or 15 terms, you can add them together. But then you're also going to see in a little bit that there's a possibility for infinite geometric sequences and actually summing them up, which is kind of a neat idea if you think about it. We're going to start with finite though. So if you have a finite sequence, or you're told how many terms it is that you're adding up, our formula is going to be S sub n, again, where n represents how many terms there are, equals A1, so first term, times the quantity of 1 minus r to the n power over 1 minus r. Okay, so you need to know the first term, you need to know r, and you need to know how many terms there are. The big difference between this and arithmetic is that, remember, with arithmetic, we also had to know how many, or what that last term was, because we were adding the first and the last together. This one, we don't need to know that. We just need to know how many terms, what's r, and then what's n. Okay, so let's go ahead and find the sum of this series, which is in sigma notation right now. First off, I can tell it's geometric just because of the format. Remember, we're looking at something exponential. So I've got 4 times 0.3 to the n. That looks pretty exponential to me. I know it's geometric. So I need to know those 3 items. I need to know A1, I need to know R, and I need to know what n is. Let's start with the easy one. What's n? This sequence is running by plugging in 1 to 12. So that's 12 terms worth. Okay. Remember, if it starts with a number other than 1, then do the top minus the bottom plus 1 to figure out what your n value is. Okay, so n is 12. Now I need to know what A1 is. What is that first term? So if I plug in 1 for n, that means my first term is 4 times 0.3 to the first. Oops, I put the first in the really wrong spot. There we go. Which is just 4 times 0.3, so that's 1.2. Okay, and then for r, now we have a couple of different ways we could find r. We could find a second term in the sequence. We could go ahead and plug in 2 and then decide what it is that we multiplied by to get from A1 to A2. But think about an exponential function. An exponential function has a starting value. So if I plugged in 0, I would get 4 as an answer. And then this number that's being raised to the power is your change. And that's what's being multiplied in an exponential function. So that number there is r. Okay, whatever's being raised to the power is your r. So that's a nice, easy way to think about that. So we have everything we need. We have A1, we have r, we have n. Let's go ahead and find our sum. So the sum of the first 12 terms, A1, which is 1.2, and then I have 1 minus r, so 1 minus 0.3 to the 12th power, over 1 minus r again, which is 1 minus 0.3. Okay, so this I am going to grab my calculator for. Let's see if I can pull them up here. Oh, look, both on the same screen. And I'm just going to type that in because I want you to be careful about how you type it in. So 1.2, parentheses. Now this fraction is kind of a complex fraction. So what I'm going to ask that you do is put parentheses around both the top and the bottom. If you do not do that, you will not get the right answer, okay? Because it's just going to take the last term divided by the first in that fraction. So parentheses around the top, parentheses around the bottom. And actually, I don't even need that extra big set anymore, but I can leave it. So parenthesis for the top, 1 minus 0.3 to the 12th. Close the parentheses around the top, divided by parentheses around the bottom, 1 minus 0.3, close the bottom, I can close the whole thing, and there is my sum. So 1.71 would be my sum. Okay, so nothing crazy, nothing tricky. We're just plugging into a formula. But in your calculator, just make sure you get those extra parentheses around both the numerator and denominator. So as I alluded to on the last sum video, we do have a possibility of finding the sum of an infinite geometric sequence. So even if a sequence has an unlimited or infinite number of terms, we can actually find the sum of it. And I know it seems a little wacky, but I just wanted to show you this picture that kind of shows how it works. So let's say we have a sequence built of the numbers starting with a half, and then we are continuing to multiply by a half to get the next term. So first term is a half, and then r is a half. So we're going 1/2 to 1/4 to 1/8 to 1/16 to 1/32, and so on. So if we go to add all these together, do you see how they would stay contained within this square? Right? They're these little blue square things up there, and that we're continuing to add terms are so small that they're never going to jump out of that box. They're going to stay within that value. And this value is the half on the left side, and then the right side, it looks like it's going to be getting really close to a half. So we would have a total sum of 1. So as long as your numbers are getting smaller as you go, as long as your R value is less than 1, then we can find the sum of an infinite series. Okay, that's called a converging series. They're all getting really, really close to something. If a series is getting bigger as it goes, if I went from 2 to 4 to 8 to 16 to 32, etc., then there's no way we can add those numbers together. That's called a diverging series, and it has no sum. So anyway, for the formula, if you have an infinite geometric sequence that you are trying to find the sum of, we're going to say S, no subscript because it's infinite, equals, all you need is the first term, and then divide that by 1 minus r. Okay, so it's simply first term over 1 minus r. We don't need to know how many terms there are because it's infinite, right? All we need to know the first term in r. And again, this only works if your r value, and I'm putting in an absolute value because it doesn't matter whether it's positive or negative, if that r value is less than 1. So your numbers in your sequence have to be getting smaller. Okay, if they're growing, this will not work and you have no sum. Okay, so let's look at this example. I've got sigma 1 to infinity, so I can see it's infinite, 4 times 1/5 to the k. And I just see that I've chosen k as a variable. It doesn't matter. That's just, whatever. So first off, we know it's geometric because it looks like an exponential function in which we've got an exponent that's a variable. So I just need to know two things. I need to know what's my first term, and I need to know what r is. So first term I'm going to get by plugging 1 in for k. So that's just 4 times a fifth, or 4/5. And then r, remember, is just that number that's being raised to the power. So r is 1/5. Okay, so now we can go ahead and find our sum. Sum equals a1 divided by 1 minus 1/5, which would be equal to 4/5 over 1 minus a fifth is another 4/5. So it looks like on this one, we have a sum of 1. Now, don't be mistaken in thinking that your sums will always be 1 with these infinite guys. I just happen to have 2 different examples here where that worked, okay? So these are not always the case, but just make sure you're finding first term and doing 1 minus that r value in the denominator. But again, only if your ratio is less than 1. Your numbers are getting smaller.